So it's probably better you guys all now know what it is, at least the instruments look like, the ones that didn't before. So we all did the above water, and if you remember, just before lunch we talked about this, the RS. The remote sensing reflectance is the L measured that you have from the surface, the LT that you had, minus whatever the little glitter is, whatever you think is reflected from the surface. And that would be the sky radiance, the radiance we have from that measurement, times the reflectivity of the surface. You're going to get a file with all of the radiances in it in the Dropbox or in wherever you guys get data. And so you should have that. One thing I wanted to mention was somebody else mentioned there's another way you can do this that's not the best but is cheaper, is with an uncalibrated radiance sensor. You'll see people doing this with an ASD where it's uncalibrated. And what they do then is they measure LT, L sky, and then they take a irradiance plaque, a spectralon plaque, and look at that and measure the radiance from that. So we'll say radiance from the plaque. If you have a spectralon plaque and you assume that it's Lambertian, that the radiance per unit, or if you illuminated it with irradiance, the radiance per unit, as you fall off an angle per unit area, it falls off as a cosine of this angle. So basically it's a very good diffuser. If you have a spectralon plaque like that, what people say is that you look at it with the sky irradiance falling on it, okay? And this radiance that you measure from that, the radiance of the plaque, is going to equal to E sky divided by pi, okay? That's if it's a perfectly Lambertian surface. When you put this all together, what you have is, what you want is LW, and it's equal to LT minus rho L sky divided by ES to get RRS, the remote sensing reflectance. If you put all this together and you have an uncalibrated sensor, then you can say that this is equal to some calibration coefficient times the number of counts you get from the plaque. You can say this is the same calibration coefficient times the number of counts you get from the total. This is equal to the calibration coefficient times the number of the plaques from the sky. Put it all together, and remote sensing reflectance is equal to K pound counts total minus rho K pound sky divided by K pi counts plaque. And if you note, that calibration number cancels in each of the terms. So you don't have to have a calibrated system. You just have to be able to make all these measurements, and you can get remote sensing reflectance. Now, the problem there, I won't go into it real far, but I haven't seen yet a person who can hold an instrument above the plaque without shadowing it in some manner or other, blocking part of the sky. They do it on ships. There's bright things all around on the ships. You should see the pictures of people doing this. I saw a picture of them doing it on a cruise that was supposedly a pretty good calibration validation cruise. And you had a whole group, like 8 people around the plaque trying to measure it simultaneously. Okay, how much does that really make sense? They're all looking at different angles of the plaque. You know, it's sort of, I haven't really seen anybody who does it, figured out a way to do it that makes a lot of sense, but it's uncalibrated.
This is exactly how it's exactly the same.
Yeah, that's why you can get rid of not worrying about the calibration of your phone. So it's got a lot of caveats in there, but it is a way to do the measurement without having a calibrated sensor, inexpensively. And a lot of times for people working in limnology, say, or in a lot of environments, that may not be the biggest uncertainty you're dealing with, so you might be able to live with it. Okay?
The other thing is, often you see they have a long cable, an optical
The,
fiber optic. And these fiber optics, if you flex them, you can get different numbers.
yeah.
And you see these fiber optics running on the ship, and then it goes in all directions, and you wonder.
Yeah. The other, I should also say, we'll talk about polarization later, but you really want to make sure that your sensors, unless you really explicitly want polarization of the surface, you want to make sure all of your sensors you're using are not polarization sensitive. Because we saw in the lab, that surfaces, reflection from a surface is highly polarized, right? Even diffuse surfaces.
Describe the radiance with the calibration factor and what's the other?
This
Okay, and then,
K, and then this is counts.
oh, count.
Counts from this when you're looking at the sky, or counts when you're looking at the target, or counts when you're looking at the plaque. Okay? Makes sense? Okay. So there's above water. Any other questions about above water? You guys all did it. You did a whole suite of angles. I'm sure Kurt's paper is in there. You might look in there to see what he says about some of those angles and the reflection coefficient and see whether, yeah.
So remember, because the way it's mounted, you're never going to get a 0.
Yeah,
or
there's
a
some
180.
you couldn't get, right?
Yeah, like even if you mounted it on the corner, right, you'd still only get 180 but not 0.
Yeah.
How do you deal with that?
That was for the lab, so you could see these different directions.
Only going
You would
there.
never normally ever want to look at 0 azimuth and look at because all you're going to be looking at is the surface glitter. Okay, that's going to be totally dominated. That wouldn't make sense. 180. Trying to think of why you'd want to look there. You probably don't want to look there because the sun. That means the sun's over your shoulder, right? And you're on a ship. You're looking there. The sun's over there, so you're looking in the shadow of the ship. So that's probably not a good place to look either, in general.
So you'd mostly only use one of these.
The recommended was the 135. People use 90 because, in a way, it's easier on a boat to put yourself 90 degrees from the sun rather than 135 degrees from the sun. So some people say 90 is better. Some people say 45, 90, because then it's easier to get 45 and it's easier to get 90 than these other angles. That makes sense? So in some ships, you're never going to get 40, 135. You can't for some other reason. Okay, and you want to be high enough on a ship so you're averaging a lot of the surface. The measurement we made wasn't very good, that low to the surface, because it's not averaging over much of the surface, but you deal with what you got. Okay. Better than if stand on the dock and been working next to that generator the whole time. So, okay, so there's that. In-water techniques to get the remote sensing reflectance. What you have to do then is you have to, you're going to make some measurement. So here's the surface. You're going to make some measurement of the upwelling radiance with your radiometer. You have to multiply it by the transmission of the air-water interface. Oops. So you're going to get some transmission of this surface. The number typically used is 0.543. In general, that seems to work pretty well. If you get really good at it and want to have really low uncertainties, there's actually a spectral dependence on that you should probably use. But in general, that's probably a good number. That takes into account the index of refraction variation, transition between in the water and the air, and it also takes into account Fresnel reflectance through the surface. Okay, so that's the TAW term. And then remember, so that gets it there. You have to propagate from here to the surface. That's using that transmission factor TZ, which to go from here to here, TZ is, if it's in the numerator, it would be exp of if the numerator would be plus the diffuse attenuation coefficient for radiance times z to bring it to the surface. So those people who are in the water, you did a profile, I hope, to get what KL was. And so you combine all those things together and you get remote sensor reflectance there, yeah.
TAW, where's that come from?
That's calculated effectively.
Analytically or empirically?
Theoretically, really. There's a paper I just published that has the spectral dependence stuff on it, but you can calculate it from just knowing the index of refraction of the water and the index of refraction of air. And then there's a paper Kurt and Preissendorfer did years and years ago that Howard realized by looking at what's it called, inversion, looking at it. So, the photon goes one way and goes the other way the same way. I forget what that's called. I lost my brain. Reciprocity. Through reciprocity, you can sort of show that wavy surfaces don't really. The calculation was done for flat and for wavy surfaces, but wasn't done for this situation. But through reciprocity, Howard Gordon showed that you could apply it to this situation of a light radiance coming up through the surface. So the waviness doesn't matter. There's also a group, Xiangping Li and Bob Arnone and some others, maybe Emmanuel was on it, I don't remember, that did it experimentally. But the problem with doing it experimentally is your uncertainty then is determined by what your uncertainty is in your experiment. And that's like that was like 10% in their experiment, where they compared above water measurements with doing this through the surface. Their uncertainty was 10%, which is more uncertainty than you can deal with in most of these. So it can be calculated effectively, is what I should say. Measure ES above the surface. There's a lot of references for it. So any questions on this part? So when you did the TSRB configuration, you basically have to take the LU measurement. Did you measure the distance between the sensor and where it was floating? Okay, so you have to take the KL that you got with the profiling and then propagate that radiance that you measure to the surface using that KL, okay? And then apply this transmission coefficient and then hope that I was measuring ES, or they were measuring ES at the same time that you were taking that measurement, okay? Oh, no, you have ES on the TSRB. What's the problem with that ES measurement? It's in air. And why is that a problem? Okay. So that measurement, that's a profiling instrument. So what do you think Emmanuel bought to put on a profiling in terms of an irradiance sensor? He bought an in-water cosine collector, not an in-air cosine collector. So it's not going to be great, except where was the sun the whole time we were doing it? Really high. So probably it's pretty good. It's not going to have a big error because of that. What's that?
Why don't we use ES that was measuring on the other guy?
You could use ES. What would be an interesting thing I'd love to see somebody do is take that data set and the other data set and compare the ESs that you measure to see how different they are between the two. Okay, that would be a great thing to do, to match up those two data sets. And the time, you have to do the time between the two. Okay? That's one thing I'd love to see somebody do with that. Okay, so any questions on this part? There's a new technique, relatively new now, although I guess it was rediscovered. Somebody else had suggested it several years ago. And that's the SBA, which is skylight blocked approach that Xiangping Li is promoting. Basically, well, you did that. Didn't you do that in the in-water? So the idea there, Xiangping Li's idea, and this other one, is that if you have a radiometer here, the problem with the above water measurement is you have to worry about the surface reflectance. So let's just block that out. Now I don't have to worry about transmission through the surface. I have the skylight blocked out, so this is basically exactly what you want, LW, okay? So it should be really good. There's issues because of shading and stuff like that, and making sure that you don't get water on this window and stuff. But it should be a pretty simple, straightforward measure to do. So that's a new technique that people are talking about. And I just mentioned that another factor you'll see, instead of LW, which is just LW divided by ES, you'll see normalized water leaving radiance, which tries to multiply it by some known extraterrestrial solar radiancy 0 divided by the Earth-Sun distance that varies a few percent throughout the year, r squared. So you'll see the term normalized. And also, whenever you see the term normalized water leaving reflectance, radiance, you want to find out for sure what definition they're using, because there's several definitions floating around for people use. Okay, there's a couple other things I want to do, and I'm done. Then Kirk can talk. When I showed you the pictures of the radiance distribution, the radiance distribution was not isotropic, right? For clear waters, the upwelling was fairly flat, but for turbid waters, it was more cupped. There was shape to it. It was brighter toward the horizon than it was down. The satellite, when it's making a measurement, measures at various different angles. And for a long time, people sort of ignored that idea that the satellite view angle will cause a different geometry than what we were measuring. Morel and Gentili, and then had a series of papers, and it culminated with a paper by Morel, Antoine, and Gentili, I think was the order, in 2002, and they started talking about this F over Q factor to try to adjust for the fact that we're not always measuring at solar noon with the sun right overhead and directly looking down. Okay, so they try to correct for both of those things. So where do those things come from? The factor F comes from, first, the irradiance reflectance R is simply EU over ED. That's called the albedo a lot of times. You see this a lot, especially in the French. We're really up on irradiance reflectance. Because if you think about it, in the old days when you had a spectrometer, it was really expensive. You can measure EU and then flip it over and measure ED or vice versa. So you had one radiometer, you were doing both. And also because then the calibration disappears from the radiometer if you're measuring both the same problem. So the French especially were interested in this EU over ED and still keep it going. It's in Maris and processing and such. So EU over ED. You saw the problem with EU though. The cosine collectors aren't very good for EU. So that's we don't tend to do it as much. An approximation, I think it started with Gordon, was that the reflectance, to relate this reflectance, EU over ED, to BB over A reasonable first guess is 0.33 BB over A. Okay, so just a quick rule of thumb that isn't perfect. And these numbers all depend on solar zenith angle and other things, but sort of rule of thumb was this, and he got it from a bunch of Monte Carlo calculations. But the main thing is that you can relate EU over ED, the reflectance, to BB over A, and inherent optical properties of the water, times some factor. Okay, so that factor is symbolized as F, little f, and so that's the F over Q part of F, the Q part of that. The other part, the Q factor, is equal to EU. It's defined as EU over LU, with the idea, remember that plaque I just showed you? Q times LU is equal to EU. And if you have a Lambertian surface, Q is equal to pi. In general, for the water, Q ranges from about 3.5 to about 5, somewhere there, or 6 or 7 if the water is really absorbing. So this Q factor relates EU over LU. So we put the whole thing together. We get F is equal to EU over ED times A over BB. And if I divide that by Q, okay, so I want to take inverse of this, LU over EU, this cancels that, we get F over Q is equal to A over BB LU over ED, okay? Or switching it around a little bit, BB over A, BB over A times ED over LU could equal to A. No, I already did that. Okay, what do I want to do? I'm moving this over to this side. Okay. A over BB is equal to F over Q times ED over LU. And what's ED over LU? Sort of the inverse of something I've been talking about. It's the inverse of the remote sensing reflectance. So it relates F over Q times this remote sensing divided by the remote sensing reflectance would give you A over BB, which is supposedly an inherent optical property, is an apparent optical an inherent optical property. So if you have the right F over Q for your solar geometry situation, you can convert it to something that's supposed to be a constant. Okay, so presumably the F over Q corrects for all the geometry problems here, and causes it to be this constant. So what does that do for you? Yeah, it's no longer dependent on solar geometry. Okay, so it's not a constant. It doesn't depend on solar geometry. So now I can compare different measurements together. No. I probably did say it wrong, thank you, but that's what I meant. It's a constant for that water. So to relate measurements at one angle to some at another, say nadir angle, you take the ratio of this F over Q for the given solar geometry you have in the given view directions. These are theta and phi for view. This is solar zenith angle. And divide it by the one for the same solar zenith angle in 0, 0, and this would correct any other view angle for that day, that solar angle, to be at nadir. Okay, so that's a correction to correct some other view angle to be at nadir. And if you want the full-blown correction, which is called then the exact water leaving radiance, you take F over Q at the solar zenith angle you measured, the theta and the phi relative to the solar zenith angle, solar direction, divided by F over Q of 0, and that would give you L of 0, 0, 0. The same rate, the radiance you would get if the sun was directly overhead and you were viewing directly down below you. Okay, and so if you want to move from one angle correction to another direction, this F over Q factor is what you need to use. There's a series of papers culminating with Morel, Antoine, and Gentili, 2002, that Morel had. There's a paper that I did with Andre that was a validation using my new rad system of this in case 1. Morel, Antoine, Gentili's was for case 1, included Raman emission, but was for case 1. Lee has a paper, Xiangping Li has a paper where he tried to do, or he's doing a correction based on IOPs rather than on chlorophyll as an index for case 1, and the idea is that can extend it into case 2 areas where you know AOPs. Fan, and this is Stamnis's graduate student, and Stamnis have a paper that they use a neural network method to correct the bidirectional effects, including with case 2 waters. And this is a paper Art Gleason and I and Howard, I think, and so a bunch of others did, where we tried to see how well this correction worked in case 2 waters as opposed to the Morel if you try to extend it and use it in the case 2 waters. So that's what's happened. We didn't know how to do, well, this paper was after that, and I still don't know how you apply a neural network that someone else develops to your own data set. I don't understand how transmittable those are. But you guys probably know more about that than I do. Last thing, I think, shadowing. You put an instrument in the water or stand on a ship at the sea or dock in the river and you're shadowing some volume of the water. We'd like to measure the outgoing light field, which means we're having an instrument above what we're trying to measure. So we're going to be shadowing something either by the ship or by the instrument. The main things from studies that have looked into it is try to avoid ship shadow. It sounds stupid, but up until 20 years ago, the way you deployed an instrument was off a crane off the side of the ship, and you didn't have a lot of choice, so you couldn't get very far from the ship. Now we have the profiling systems that will show at sea, the one you used here, and a COPS, and that allows you to drift it away from the ship and get a better measurement, so that's good. If you're stuck with a ship, you definitely want to be on the sunny side of the ship. People go to the, okay, well there's that. Instrument shadow, the instrument itself is going to do it. Shadowing to first order, it's proportional to the absorption times the radius of the instrument if you have a symmetric instrument. So you want to use as small an instrument as possible, especially if you're working in here where there's a high absorption or in some place where there's high absorption. To make a measurement in a red that's good, you probably, like at 700 nanometers, say, you probably need to have a fiber optic way away from anything else, okay, to keep from having a shadow effect in there. There's people that go, we were talking about in-water protocols in Lisbon at this workshop, and people like Giuseppe will take that profiling instrument that you played with here, and they'll figure out, if the sun's over here, they'll figure out, the wing is typically going to be perpendicular to the ship. If you're deploying it off the stern of the ship, the wing will typically be perpendicular like this to that direction. They'll make sure the radiance sensor is on the side of the sun. They'll flip the instrument around to make it work right.
We talked about it.
What's that? Oh, you talked about it here? Oh, good, good. So there's that. I forgot, there's one more thing. Oh, there's a bunch of papers about corrections for shadowing effect. Sun photometry. I told you everything on this slide already when for everybody I talked to individually almost. Okay, so we all got that part down. But what do you do with the measurement? The idea is that if you have the extraterrestrial solar irradiance. So there's the top of the atmosphere. Here's the bottom of the atmosphere. Here's 1 atmosphere distance. The light's coming in here through some slant path. Here's the sun. This is a solar zenith angle, theta 0. Light's coming in through some path length here, and you know that this distance is actually equal to 1 atmosphere, which will define this as unit 1 atmosphere. This distance is 1 over cosine of the solar zenith angle, roughly. Okay? And if I know E0 up here from a table, and I measure my irradiance, direct solar irradiance at the bottom, then the transmission is just E over E0. And this is equal to the exponent e to the minus this term, the aerosol, or the total optical depth, tau, times m. And m is called the air mass. Okay? So, you measure the irradiance at the bottom, direct solar irradiance at the bottom, divide it by the outside, and you can work with this equation to get the optical depth up there. Same thing as you've been doing with absorption and scattering. What's that? No, so I didn't put in lambdas. It's spectrally dependent all the way through.
Is this a diffuse attenuation that's in the tau, or is it limit attenuation?
It isn't. I guess if you wanted to use LiDAR terms, I might call it a system attenuation. It includes scattering. You have a 2-degree field of view, so it includes scattering between 0 and 1 degree. Okay, in there. So part of what they call the scattering at small angles is the aureole, the solar aureole, the small angle scattering, and so it includes a little bit of that. And that's basically to make the instrument practical to use. The radiance from this falls off is like 10 to the 7th or so from on the disk to right off the disk. So having that, you don't make much of an error by including that 2 degrees. So the standard is 2-degree field of view. Okay. All right. So there's that. People ask how you calibrate it. You can either have a calibration number that already tells you what this number is in instrument units. The other thing is if you plot, as I did there, if you plot log of your measurement versus air mass, okay, and if you're really good and have a very good stable atmosphere, you get a nice linear relationship like this. The slope of this line is equal to minus the optical depth, okay? And the intercept of this line at 0 air mass is actually log of E0, okay? And so if you had a really good day where you could make measurements as the sun went down or came up, you could get a measurement of log of the counts that you have here versus air mass, plotted up like this. This is called a Langley plot. Yeah, Langley technique. And it'll tell you both the aerosol optical depth and also tell you the intercept that then you can use any other day to get the calibration. Okay, so what you should do with the data that I'll upload is make this plot of log of the irradiance. It'll give you irradiance out versus air mass. It'll also calculate the air mass for you. Okay? Yeah.
So the vibration in the atmosphere is related to the density.
So the attenuation in the atmosphere is related to, well, attenuation has Rayleigh scattering in it. So scattering from molecules in the atmosphere, roughly. And that's proportional to the surface pressure that we do, but in general, it's, and there's gas absorption that will occur. Ozone absorbs in certain wavelengths. Nitrogen absorbs in certain wavelengths. And then aerosols in the atmosphere. So the amount of aerosols, but that also, it's not just the concentration, but it's the size distribution of the aerosols. Scattering, too, affects what their attenuation is. Okay? So what people, to get an idea, just like we were doing with scattering, in fact, this thing you're doing with scattering came with particles in the ocean, came from basically the atmospheric guys, is the idea that they looked at the aerosol optical depth. So this total optical depth, after you subtract Rayleigh scattering and any gas absorption you know, what's left is aerosol optical depth. You plot that versus wavelength, and you'll get the same thing as you got in scattering. You'll get you can get a relationship that looks like an angstrom law. And the angstrom law came from aerosol studies, really. Okay, so it's spectrally, the scattering is spectrally, the attenuation is spectrally dependent for aerosols, and you can get an idea of the size distribution by looking at how that varies.
What I was thinking that in water you get an exponential attenuation of the light. So in the atmosphere, it won't be related to the height, but to the density.
Well, as you get more air, yeah. When you go to different altitudes, the Rayleigh component here Okay, so the total optical depth could equal the optical depth due to the Rayleigh plus the optical depth due to molecules absorption plus the molecular or the optical depth due to aerosols. Okay? This component in particular, if you're going to different altitudes, the Rayleigh part will change because as your pressure decreases, there's less above you, and so that will go down, and that then feeds into this transmission term, just like the other. That right? That makes sense?
What are those three terms again?
Rayleigh optical depth because of molecular scattering in the atmosphere, molecular some absorption, gas absorption that you might know about, and then the remainder is aerosol scattering and absorption. This is the big deal with here is that it's highly variable from place to place because the aerosols typically hang out in the lower first kilometer or so of the atmosphere where also it rains a lot, water, clouds and everything. And so they're both highly variable because of source dependence, and they also don't necessarily last real long in the atmosphere, or so they're highly spatially and temporally varying, and yet they can have a large effect on climate through different effects. And so this is a big problem, or still an unknown for climate, or one of the places we justify making the measurements because of climate.
So the instrument, which wavelength did it measure?
People ask that, and I'll tell you. You'll see in the data file. I can't remember which 5 wavelengths. There's 5 wavelengths. Each of the instruments measured 5 wavelengths, and I can't remember where they are. One's a water vapor line, but the other ones I can't. Typically, you put them at wavelengths that don't have a high gas absorption, so that's not a big variable. So you try to pick them like that. Okay? Okay. I think that's it. So, yeah. Anything else? Sorry I took so long. So, okay. What do we plan? Quarter to 5.